Hey, chemistry crew, Mr. Collier here. In today's notes, I want to talk about pH is sort of the main thing. And this is something where we can help talk about how strong an acid or a base is and sort of what its actual properties are a little bit numerically. So the first thing I want to just sort of show and remind you of is that an acid or a base, when it ionizes, it is dissociating typically in water to have some ions. And so like here's sulfuric acid, H2SO4. And when that dissolves in water, you're going to have two hydrogen ions zipping around, probably forming hydronium, right? Kind of donating themselves to water molecules and becoming H3O, and then some sulfate ions. So this dissociation is going to tell us a little bit about how many hydrogen ions there are floating around, and sort of it's going to dictate a little bit the strength of the acid or base. So here's calcium hydroxide with two hydroxides for every calcium. Now, what happens is that water is something called amphoteric. It can react as an acid and a base in the same situation, in the same reaction, because it can be water, right? But it can also gain hydrogen to become hydronium or lose hydrogen to become hydroxide. In pure water, this is actually happening. So even in water that's just sitting there looking like plain old water, you're going to have hydronium and hydroxide ions both be found within that water, and they're going to be found equally in concentrations of 1 × 10⁻⁷ molar, right? So we talked about concentrations in our solution. Because they're at equilibrium, right? And we're not going to include water when we talk about this equilibrium expression. What we end up with is this nice little equation where the concentration of these is simply this. Okay, and we're going to show you a little bit more about that. We're not going to get too deep into this math here, but here's this general idea, right? So we know that they are each 1 × 10⁻⁷ molar. And when we multiply 1 × 10⁻⁷ molar by itself, we get 1 × 10⁻⁴ molar. That is our equilibrium constant for water. It's this magical number that when we multiply those concentrations, if things are at equilibrium, those concentrations will multiply out to this value. What that means is if the concentration of one thing goes up, then the other has to go down, because this equilibrium constant is a constant. It has to stay at that value. So we can use this to calculate the concentration of things. If we know one, what's the other? And then we can determine, is it an acid, is it a base, or is it neutral, right? So we can typically, we take this starting point and we rearrange it, right? So if we want to know the OH concentration, right, the hydroxide concentration, we simply take Kw and divide it by hydronium. So we're just rearranging, right? So then you get the known constant divided by the concentration of the other, and it's going to tell you the concentration of the unknown, in this case hydroxide. And then it asks us, is this an acid or a base? And so this comes back to what's stronger in concentration, hydroxide or hydronium. If the hydroxide is higher in concentration, which is the case here, 10⁻⁷ is a bigger number than 10⁸, then it's going to be basic. And this is actually how we're going to determine whether something's an acid or a base, is based on its concentration. Things that are high in hydronium concentration have got extra hydrogens floating around ready to be donated. That's the definition of an acid. Things with extra hydroxides in them are sitting around ready to accept more hydrogen ions, and that's the definition of a base. So by looking at these concentrations, we can determine whether something's an acid or a base. Now, That's a little bit of a pain in the butt to be sitting there calculating concentrations. So we have a sort of a shorthand to talk about whether something's an acid or a base, whether its concentrations of hydronium or hydroxide are higher. We call this the pH scale. The pH scale is simply used to determine whether something's an acid or a base and the strength of that acid or base based on its hydronium concentrations. So specifically, the pH scale is hydronium concentrations on a logarithmic scale. What logarithms mean is that the pH scale is changing by a factor of 10. So something with a pH of 7 versus a pH of 8, they're not different by 1, they're different by a power of 10. And a 7 to a, say, 5, right, a jump of 2 is actually a jump of 10 to the 2. It's a jump of 100 times. So if 10,000 is 10 to the 4th, we would say that the log of 10,000 is 4, right? The log becomes like what the exponent is, right? A little review of logs for math class. And I'll post some extra videos on this for some help just about logs and how to use them in your calculator and stuff like that. So 0.001 is 10 to the negative third. So the log of 0.001 is 10 to the as negative 3. So the pH is typically going to be dealing with these very small concentrations. And so we're going to have these little negative exponents, but we usually are going to just report this as the positive value. Anything with a pH of 1 to 6.9 is considered an acid, right? And anything with a pH of 7.1 to 14 is considered a base, and a pH of exactly 7 is neutral. Oh, hey, I remember just when we were doing that, the the concentration of hydronium and hydroxide in natural pure water is 10 to the negative 7th. That's where that comes from, right? That neutral, that's the sort of starting point. So we can calculate the pH by doing the negative log of the hydronium ions, right? The hydronium is for pH, and it's the negative log because we're actually dealing with really small numbers like 0.001. And so instead of calling the pH -3, we just call it 3 by saying that it's the negative log. That's how we end up with a positive number. And the hydronium multiplied by the hydroxide concentrations is going to be 10 to the negative 14th. And we can put all these together to start doing some math. There's also POH, which we're not going to talk about right now, which talks about hydroxide concentrations instead of hydronium. So let's take a look at a scale here. This is an interesting little chart where you've got, if something is a very strong base, you would have a pH of 14, you would have pretty much no hydronium ions, a very, very low concentration, and a very, very high concentration of hydroxide concentration. That's up here, boom, all hydroxide. In the middle, we've got neutral, where those are equal, and that would be here, right? This is equal to this. And so that's a pH of 7 when they are balanced. The hydronium and hydroxide are about the same, so it could go either way still. And a strong acid is the other way, where we've got all hydronium and very little hydroxide. So there's lots of things in life, right? Not just stuff in the lab that is either an acid or a base. We've got things that are neutral, that would be your pure water. And then actually in life, things tend to be either more acidic or more basic, right? So something that we can drink is tomato juice or coffee. Those are both slightly acidic. And as we get there, we get things that we think of as, ooh, that's really acidic, like lemon juice, but then actually it gets way more intense than that, where like the hydrochloric acid in your stomach that's dissolving your food is even more acidic than that. And then we can get to these really concentrated hydrochloric acids, right? Which sometimes we use hydrochloric acid in labs. And going the other way, we can get things that are basic. And you'll notice something like milk of magnesia, right? That's something that you drink to calm an upset stomach. That is because you've got acid in your stomach and you want to make a neutralization reaction. We've got sodium hydroxide, which is a thing that we use in the lab as our kind of go-to base. Ammonia, which you have in your household, is a base. That's a cleaning product. So just some different common acids and bases. When you're doing these calculations with significant digits, with acids and bases, you should, and this is weird, but it's important. It's the number of digits after the decimal point that should be equal to the number of significant digits in your original number. So this is special just for logs. Okay, so this is a rule for logarithms. So 8.7, right, has 2 significant digits in the original number. And so what we're going to do is after we take the negative log of that, we're going to round it off to 2 significant digits after the decimal. So we take the digits in the original number that we're taking the log of, and then we're going to put that many digits after the decimal. So that's the rule for that. So we can take something that has a hydronium concentration of 7.3 times 10 to the negative fifth, and we can say, is this an acid, a base, or a neutral, and what is its pH? To figure out the pH, we're simply going to take the negative log of 7.3 times 10 to the negative fifth, and we're going to get this value, 4.14. 7.3 had 2 digits, so I give 2 digits after the decimal. 4.14 is an acid because it's less than 7. Okay, there's your sig digs. And that's the basic idea. Another example would be, what if we had hydroxide instead of hydronium? Well, now, to do pH, we're looking for hydronium, not hydroxide. So first we need to do that rearranging of the equilibrium equation, right, to solve for hydronium, because that's what we care about. So hydronium is 1 times 10 to the negative 14th. That's that equilibrium constant divided by the hydroxide concentration. And that's going to give us the hydronium concentration. Now we're ready to take the negative log. So we take the negative log of that value, and that gives us the pH. It is above 7, so it is a base. Okay. That is where we're going to stop here. That's the general idea about pHs and acids and bases.